Hello again. We are going to continue our journey in organic chemistry by looking at Chapter 8, which will discuss the functional groups of alcohols, ethers, and thiols. A lot of this you're going to find to be review from the previous chapters, namely alkene additions and eliminations and substitutions, especially with the alcohol portions. So just bear in mind that these are topics that you should be somewhat familiar with as we go through this chapter rather quickly. So I am going to share my screen. And get rid of me. All right. So let's talk alcohols, ethers, and thiols. Remember, the functional group of an alcohol is the OH or hydroxyl group. And this is bonded to an sp3 hybridized carbon. So remember, I have those idealized, basically idealized bond angles on that carbon of 109.5. The oxygen itself is also sp3 hybridized. So each of those lone pairs is residing in an sp3 hybrid orbital. And I have two sp3 hybrid orbitals that form those sigma bonds to the carbon and the hydrogen atoms. So again, let's reiterate. I have two sp3 hybrid orbitals that form the sigma bonds between the oxygen and the carbon and the oxygen and the hydrogen. And I have two sp3 hybrid orbitals that each contain an unshared or lone pair of electrons. So I do have my tetrahedral angles in all of these different atoms. My bond angles are going to be just slightly off of tetrahedral because of sizes of atoms and the size of the methyl group and whatnot. But notice that in general, they're pretty close to that 109.5 degree bond angles. So we're really going to focus on this alcohol functional group. Remember, I have a hydrogen bonded to an oxygen, and then I have those two lone pairs. So oxygen is pretty electronegative. Oxygen has two lone pairs, and it is an electron-rich area around that oxygen atom. All right, so let's start with the nomenclature of alcohols. Again, we're going to take everything that we've learned before and we're going to expand upon that. So as usual, the parent chain is going to be the longest chain that contains the OH group. The oxygen alcohol, that functional group, is pretty high in priority. So the parent name is actually going to be called a something all. So it's going to be the alkyl chain, the alkenyl chain, the alkynyl chain, and then we're going to have that suffix, which is the all. So we're going to number this in order to give the OH group the low in number, period. It doesn't matter how many other substituents are in the structure or anything like that. I'm going to number the parent chain that contains the alcohol functionality group to give the carbon that bears the OH the lowest number. And then I'm going to change the alkyl, the E on the alkene to an all. So like I could have, 2-pentanol or 5, well, that's a large number, 3-hexenol. So I have to think about all of these different ways that I could put this together. And that's for the IUPAC names. There are common names for these as well, and they are used fairly commonly. So basically, to use the common name, I'm going to name the alkyl group that's bonded to the oxygen, and then I'm just going to follow that with the word alcohol. So like CH3OH would be called methyl alcohol. And in the IUPAC, it would be methanol. So that would be a difference between the common name and the IUPAC name. And I will tell you that the common names and the alcohol functional group are used very often. So you do have to know a lot of the simpler examples. So here's some examples of both the IUPAC, which is up in the first row, and then the common, which is in that second row. So here I have 1, 2. I have 2 carbons, so it's ethanol. Here I have 1, 2, 3. Notice now I have to indicate location, because if it's on the 1 carbon or the 2 carbon, I get 2 different constitutional or isomers. So as my carbon chain number increases, I have more possibilities for constitutional isomerism. So don't forget that part. But notice in the common name, that's an ethyl group. This 2 carbon chain is an ethyl group, so it's called ethyl alcohol. This 3 carbon chain is a propyl group, so it's called propyl alcohol. This is my whale tail here, which is my isopropyl. That's the alkyl group, so it's called an isopropyl alcohol. This is my long, continuously connected butyl, so it would just be butyl alcohol. Notice this group is sec-butyl alcohol. This group is isobutyl alcohol. This group is tert-butyl alcohol. And then here I have cyclohexyl alcohol. So these common names for these examples that are in this slide are things that you need to know, because those common names are used extremely often in order to refer to these particular molecules. You can also see that as I do the IUPAC route, I do have to indicate locations for where my alcohol is or where any other substituents might be. So you have to make sure that you consider all of the different rules that we've learned for IUPAC and make sure that you incorporate them into this functional group naming procedure as well. All right, so here's an example. Write the IUPAC name of each alcohol. Okay, so in this first example, we're gonna notice that we have this CH2. So there's 6, 7, 8 carbons. So basically it's 1, 2, 3, 4, 5, 6, 7, 8. And then I have the OH. So all of these in between carbons are going to be the CH2. And then I'm going to have CH3 at the end, which is this guy here. And what I get is 1 octanol for that name. Here in B, I'm going to number to give the OH the lowest number. That means on the 4 carbon, I have a methyl substituent. It's going to be a pentanol. So I'm going to call this 4-methyl pentanol. Oops, I forgot the location. -2-pentanol. I do have to indicate what carbon that alcohol is on. So it is definitely on carbon number 2 if I number it the correct way. So that would be the name for this. Now, in C, I have an indication that I have stereochemistry. Now, if I don't want to be stereospecific and name that exact enantiomer, what I'm going to do is going to name this with geometric isomerism. The carbon in a cyclic alkanol that bears the OH is carbon number 1, and I'm going to number to give the next encountered substituent the lowest number, so I'm going to go down and around instead of up and around. So these groups are trans to one another. This is a methyl. These are trans to one another. So one possible name for this would be trans 2-methyl cyclohexanol. Now notice I don't have to do the location for that alcohol because I know in a cyclic structure like this that the carbon that bears the OH is number 1. Now, if I wanted to do something that was stereospecific here, what I need to figure out is what is the stereochemistry at those 2 carbons. So if I do this, I have priority 1, priority 2, priority 3. That carbon is going to be clockwise, so that's going to be R. And then I'm going to look at this carbon. Notice my hydrogen is sticking out at me. So whatever I get, I'm going to have to reverse because of that. So here I have priority 1, priority 2, priority 3. That is going to be counterclockwise, which is S, but I go to R because of this hydrogen is pointing out at me and it's supposed to be pointing behind me. So what I have here is 1R, 2R, 2-methyl cyclohexanol. And that would be the name that I get for this particular specific. This is naming an enantiomer which is indicated. So I'm assuming that that's a absolute configuration, and I do not have a racemic mixture. Here I'm assuming a racemic mixture, and I'm just designating the relative stereochemistry between the 2 groups. Here I am assuming that I have a stereospecific mixture, which means I only have the presence of 1 enantiomer. Okay, now let's look at this next one. This next one is easier if I draw it out. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then I have my OH. And then on this carbon, I have another 1, 2, 3. So that's going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Everything is right. So what this is going to be, I have a 2 propyl, 1 pentanol as my final name. So here's some examples for the nomenclature. Now, we can go a little further. What happens if I have a compound that contains 2 OH groups? well, that's going to be a diol. If I have 3 OH groups, that's going to be a triol. And if I have 2 OH groups on 2 adjacent carbons, that's called a glycol. So notice this one, in terms of IUPAC, is 1,2-ethane. Notice that E is there, diol, or it's called ethylene glycol. Now this is something you put in your car, which prevents freezing, right? This is antifreeze. So you have this in your garage, most likely. Here I have 1,2-propane, notice the E, diol, right? So this would be 1,2,3, 1,2-propane diol. So this gives you the location of the 2 OHs, or the common name is propylene glycol. Now this guy is pretty common, especially if you're looking at biochemistry, because this glycerol is the backbone of triglycerides and other important lipids in biochemistry, but it is a 1,2,3 propane, note the E, triol. That would be the IUPAC name, but it's also very commonly known as glycerol or glycerin. And again, it's the backbone for triacylglycerides, which are fat molecules and are important lipids in biochemistry. If I have an unsaturation in my molecule, I am going to refer to that double bond by my infix, which is ENE, which tells me that I have a double bond present, but I also have the hydroxyl group, which is now going to be that final suffix, which is the OL. So I'm going to go and number this. I have 1, 2, 3, 4, 5, 6. On my 1 carbon, this is my OL, right? This is the hexanol. And then notice on my 3 carbon, I have my hexene. So I'm locating the double bond first, and then I am putting in the alcohol. This could be also, there is stereochemistry. What I know is that this particular structure has those hydrogens trans to one another. So I must put this trans or the E designation in this particular name. Now, this could also be hex 3-ene 1-all. That would be another viable IUPAC name, because I can separate these and give the locations right before the infix and the suffix, and that's also a valid name. So don't forget that. But the key here is, if there is geometry around that double bond, you have to somehow account for that geometry and specify which isomer I actually have in my molecule. Now, physical properties of alcohols. Again, this is sort of review. I have a polar carbon-oxygen and a very polar oxygen-hydrogen bond in methanol. That means I have a partial positive on my carbon and a very partial positive on my hydrogen, and I have a partial negative on that oxygen. So if I look at this electron density map, I can clearly see that this is an area of partial negative charge. And look at the color of this blue. That tells me this is very partially positive. And then notice my carbon here is more green. Actually that's my oxygen, never mind. My carbon here is more greenish blue. So I have a partial positive, but this partial positive on the hydrogen, right, this is my hydrogen, is pretty significant. So this is sort of what it looks like when I consider the three-dimensional structure. Remember, this would be tetrahedral. This has my two lone pairs, so it's going to be tetrahedral electron geometry, but it's going to have that bent molecular geometry just like water. Remember, when I have an H bonded to an O, right, I have the capability for hydrogen bonding. So alcohols associate with each other in the liquid state by hydrogen bonding. Remember what this hydrogen bonding is. It's the attractive force between a partial positive charge on hydrogen and a partial negative charge on a nearby, very highly electronegative oxygen, nitrogen, or fluorine atom. So hydrogen's bonded to oxygen, nitrogen, or fluorine. Those are the only hydrogens that can make a hydrogen bond. The strength is pretty strong. Remember, this is my strongest intermolecular force. And just for comparison, even though hydrogen bonds are very strong in terms of intermolecular forces, they're much weaker than my normal covalent bonds. So just keep that in mind. The key here is that hydrogen bonding is strong enough where it can have a significant effect on physical properties. So we have to consider what these effects would be. Here I have ethanol molecules associating in the liquid state. So I've got hydrogen bonds here and here. The lone pair on those oxygens can accept hydrogen bonds from those hydrogen atoms. Here's the hydrogen on that center atom that can form a hydrogen bond with the oxygen on another atom. So when I look at this central atom, what you should notice is you have 3 hydrogen bonds, which are shown as these red dots. 2 through oxygen. That oxygen is accepting the hydrogen bond. And then this hydrogen is donating to the hydrogen bond. So the oxygen is acting as a hydrogen bond acceptor, and the hydrogen is acting as a hydrogen bond donor. Okay. So this hydrogen bonding is reflected in physical properties, as we've seen with water before. If I look at similarly sized alcohols and alkenes, so now the molecular weight is comparable. So I can compare apples and apples. If I notice my alcohol here, which can make a hydrogen bond, and my alkene, or alkane, which can only form London dispersion forces, notice my molecular weight is within a very narrow range. This is a extremely high boiling point for that molecular weight. Notice in my alkane, I am a gas, right? My boiling point is negative 89 degrees Celsius. So that is very, 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 very low. I have a huge increase in boiling point just by putting that OH in play, right? In fact, that methanol is actually liquid at room temperature. Notice also that this is infinitely soluble in water because my water can form hydrogen bonds with the oxygen and accept hydrogen bonds from the hydrogen. So that water has the same type of bonding, right? Remember, water is polar and it can form hydrogen bonds. And because the carbon piece is really small, right? The carbon is non-polar, but relative to the OH in methanol, that's a very small portion of the molecule, so I am infinitely soluble in water. Notice as my carbon chain increases, as my non-polar piece increases, my solubility starts to decrease as I get larger and larger and larger. So my alkyl piece is non-polar. As my non-polar portion increases, the size of the non-polar portion increases. That non-polar portion is not going to form intermolecular attractions with polar water. Remember, like dissolves like. So as my carbon chain size increases, my solubility will decrease. But notice, in every case, the boiling point is still significantly higher than the corresponding alkane. Notice if I have a diol, even when I have a higher carbon count, I go back to having infinite solubility because now I have two areas of interaction with the water molecules. I have double my chance for hydrogen bonding. And notice that increased hydrogen bonding capacity also has a drastic increase in the boiling point also. So you should be able to compare and contrast the boiling points of alcohols with other molecules, especially something like an alkane. And you should be able to sort of rank order which compound would have the lower boiling point and which would have a higher boiling point. Excuse me. By doing an analysis of this type where I'm looking at intermolecular forces. Another property of alcohols is we know from looking at water that water is called amphoteric because they can act as a base or an acid. Well, the same thing can happen with alcohols because remember, I basically have a very similar structure to water. The nature of this R is going to drastically affect the properties, but what I know is that most alcohols are about the same or slightly weaker acids than water. So here, if I look at methanol, I have a pKa of 15.5. My pKa of water is 15.7. So that is just a little bit higher. So water is going to be a little weaker. So this would look at this dissociation constant. If I did this math, I would find that my Ka value is 4 methanol is 3.2 times 10 to the minus 16, what gives me just in that this relatively the same acidity as water. Because of that, if I have aqueous solutions of alcohols, I'm going to have basically the same pH as that of water. So when I put this in my sort of pKa value chart, remember, the lower the pKa, the stronger the acid, right? And that's going to be the higher the Ka. So when I look at this, notice here's water. That methanol is just slightly increased in acidity. And these other ones are just a little bit less than water, which has that particular pKa. So methanol is just slightly more acidic, very slightly more acidic, and then most of them are either a little bit weaker acids compared to water. Now, alcohols can also act as bases. Remember, I have these lone pair. They can be Lewis bases and donate a lone pair. So when I have a strong acid, the oxygen atom of an alcohol can behave as a weak base. So here I have an example of a proton transfer reaction from the strong acid to with this base ethanol. Remember, this is electron rich. This is going to be electron poor. So my electrons are going to go from the oxygen lone pair to the hydrogen, break that bond with those electrons. Remember, those electrons are now on the water, and then I formed this new bond, which is here. This is an oxonium ion, which has a positive charge. So these are amphoteric molecules or amphiprotic, whichever you want to call it, depending on what your general chem book called it. And alcohols can function as both weak acids and weak bases depending on the conditions, very similar to water molecule. At this point, we're going to stop here, and we'll come back in a little bit and look at reactions of alcohols. So here is enough to get you started on chapter 8. I'll see you very soon.